to give first his version of introduction. So Michael Berry is a physicist of University of Bristol, where he was twice as long as he has not. So I find very smart and very modest for him. But let me also just little bit extend the introduction with my version. So Professor Sir Michael Berry is an outstanding mathematical physicist, laureate of more than 20 worldwide recognized awards and prizes, including Dirac, Maxwell, Lorentz, Kubica, Onsager, and many more medals, member of a number of national and royal societies and academies, laureate of Ig Nobel Prize 2000 in physics, shared with Andrei Game. He is known for the Berry phase, Berry curvature, Berry connection or potential, Berry-Robbins problem, Berry-Taber conjecture, Weyl-Berry conjecture, quantum carpet, quantum chaos, superoscillations, and many other concepts. In 2023, he contributed to the special issue Nanophotonics in support of Ukrainian scientists of the journal Nanophotonics with the article, wonderful article, I read it with great pleasure, Ukraine and Singular Optics. And today, I'm very happy to announce that he is given colloquium talk, quantum trajectories, quantum potential, superoscillations, Madelung, de Broglie, Newton. Please, Professor Sir Michael Berry, the floor is yours.
Right, I have to share my screen. Just a moment. Good. Can you see?
Wonderful. Yes.
Very good. What a pleasure to be part of your seminar. I only regret that I can't be with you in person for the obvious reason. I have a number of connections with Ukraine, the earliest being before I was born, when my father's parents emigrated from Odessa to London, 1906. And I've been a few times to Odessa, Kyiv, Crimea, before the Russians came, and Chernivtsi several times. So I have connections, and I'm very proud to be a foreign member of your National Academy. I'm going to talk about some old things and some very new things, including a paper not yet submitted. Here are the principal characters. First is de Broglie, whose centenary of his famous paper on matter waves was last year. And actually that really kick-started what has turned into this lecture. Einstein was very complimentary about his discovery. He has lifted a corner of the great veil. This was 1923, before, of course, quantum mechanics reached its final form. Well, then came, of course, Heisenberg and Schrödinger, but the main hero of this talk is Madelung. Erwin Madelung, I'll tell you in a moment what he did, and an unexpected connection with Isaac Newton. Now, de Broglie, his emphasis was all is waves. He emphasized that not only light, sound, water waves, phenomena are wave phenomena, but also massive particles would have waves associated with them. Just a moment. Yeah. Now, Madelung, he reinterpreted the Schrödinger equation, and indeed all wave equations, although he didn't emphasize this, in terms of what one might like to call rays. For example, here's the Helmholtz equation. I write it because it's not the usual equation one uses in Madelung, but nevertheless, it works. Here's a refractive index varying with position, and I'm thinking of the plane. That's enough for today. Well, Madelung said, write this in polar form, modulus and phase, and emphasize the local phase gradient, which is, you can call this the local wave vector. Of course, because it's a gradient, it's a curl-free vector. And the Madelung trajectories, rays or streamlines, as I'll often say, are the integral curves of this vector field. And in what he called a hydrodynamic analogy, these will be the paths of fluid particles. Now, this formalism was rediscovered later by David Bohm, and I'm not going to discuss this because that emphasizes interpretations. I'm not interested in interpretations of quantum mechanics. I'm interested in pictures of quantum mechanics, and Madelung trajectories, as you'll see, provides a very nice representation complementary to other ways of thinking of quantum waves. Now, this wave vector is the wave counterpart of the rays of geometrical optics or classical physics, but with important differences. Now, there are many reasons for taking this quantity seriously. I've written about it, a paper called 5 Momenta, local momentum, local velocity, proportional to the current. It's the mean velocity in the Wigner distribution. In a Aharonov scheme, it's the weak value of velocity with position post-selected. There are a number of different ways to see that this is an interesting quantity, this K vector. Well, Madelung showed by substituting in the Schrödinger equation, because there are two quantities, the modulus and the wave vector, there are two equations. And one is a continuity equation. The intensity times the wave vector is divergenceless. And this quantity is the current, or in optics, it's the Poynting vector or energy flow. And the other is that the local wave vector is the following. It's the wave vector you would expect from geometrical optics or classical mechanics, but plus an additional term which couples the wave vector and the modulus. And this is the wave analog of the quantum potential, and it's a kind of non-locality. And then this is exactly equivalent to the Schrödinger equation. You can think of this as proportional to an effective refractive index modified. So here it is, the external index, which could be 1 if you're in a vacuum. But then there's this additional term, and they call it the wave potential. Now, the analog of Newton's equation in this formulation is that the curvature of a ray is the logarithmic derivative of this modified refractive index perpendicular to the ray. It's a known result. And this shows that the rays can be curved even in free space because of this coupling, unless you have something very simple like plane waves. Now, there's an additional condition emphasized by Takabayashi, which is because you're speaking about the gradient of a phase, the phase must be varies by a multiple of 2 pi around any circuit. We'll come to that later. Let's have a look at this concept. Let's look at 2 plane waves. Here they are in these directions, one upwards and one diagonal, different strengths. Now, in geometrical optics, this corresponds to 2 families of rays, and here are their momenta. And there's an average momentum, the ray momentum in geometrical optics. But we're speaking about waves, so here's the same superposition, and here you see the intensity. And you see this interference, of course, emphasized by Thomas Young and developed by Fresnel. I found a beautiful quotation about this. After Thomas Young died, Arago, who worked closely with Fresnel, said, "Who would have imagined that darkness could be engendered by adding light to light? And indeed, the possibility of perfect destructive interference is one of the defining leading characteristics of wave phenomena of all kinds. It's amplitudes that add, not intensities." Well, here are the Madelung trajectories. And I've superimposed them on the phase, which is color-coded with hue. That's a natural periodic representation, very good to represent phase. So here they undulate and emphasized by several people that it's these undulations which in the Madelung picture indicate interference. So here we are, we see these undulations. Another way to express it is the superposition of momenta, what I showed you in geometrical optics, is not the same as the momentum of the superposition, because phase is a nonlinear function of a function. That's the reason why this can look very different from what you would expect in geometrical optics. Now, you don't see the full picture unless you have three plane waves. So here are three traveling in different directions, and classically you'd have this superposition and this mean momentum. But here you have the intensity, and these black places are perfect zeros. And these zeros are singularities of the phase, places where all the colors which represent constant phase meet. Okay, this is a new phenomenon that you get when you have more than two plane waves. These are phase singularities. In the old days, we called them wave dislocations, nodal sets, different names for the same thing. Well, here are the Madelung trajectories, and they form closed loops around the phase singularity. So they're also called wave vortices. And optical vortices is a very big subject now, being studied by very many people experimentally and theoretically. If you zoom in near a single vortex, you see this structure, also saddles, which we'll come to later. But here are the phase singularities, and this is half a wavelength. Very good. Now, at a vortex, the amplitude is zero, but that's in the denominator of the potential, so it diverges. So in a sense, these are the waviest places. In quantum mechanics, they're the most quantum places in a wave field. Now some history. The first phase singularities known to me were discovered in the tides by William Whewell. He was following up a suggestion of Thomas Young, which was that the tide is a wave of 12-hour period which circles the Earth, and it is complicated because it is diffracted and reflected by land and refracted by variations in the depths of the sea. And he produced this picture of the wave fronts of the tide wave. What that means is you choose a particular time and you connect all the places where the tide is high at that time. Then you wait for the next time and the next time. And he realized that using topological reasoning based on many observations, this is 1833, big international collaboration, that there are singularities, there are tideless places. He called them amphidromic points, a phase singularity of the tide waves. It's interesting that this work of Whewell, which is really scientifically very important, is not well known now. He's much better known for inventing words. He invented the word physicist and the word scientist, words that we use all the time. Well, this is now a central concept in modern oceanography. Here are the world's oceans. It's not detailed, there's even one in the Black Sea, a phase singularity. They're generic in waves of all kinds, and they're the stable singularities, stable in the sense of stable under perturbation in wave physics, much studied now. Now, I want to go back to see how Isaac Newton anticipated Madelung and almost discovered phase singularities. It's a story worth knowing. He was thinking about edge diffraction. Grimaldi had observed it, and you know that Newton had difficulty understanding diffraction because he didn't accept that light was a wave. Well, he conjectured that these interference fringes, as we call them now, that an edge might exert a force, and he asked, are not the rays of light in passing by the edges and sides of bodies bent several times backwards and forwards with a motion like that of an eel? And do not the three fringes of coloured light arise from three such bendings? Now, this was occasionally quoted, but not taken seriously until now, when we realize that Newton was exactly right 250 years later, and I want to explain how. You see, Sommerfeld had this exact solution in the 1890s of Maxwell's equations for an electromagnetic wave diffracted by a half plane. This is the mathematization of Grimaldi's edge. Well, I'm not going to give the formula, but it involves Fresnel integrals, an exact representation of, let's say, the electric field or the magnetic field. Now, Newton wanted to understand this. You see, you've got incident diffracted light, and if you look on a screen, you'll see that the shadow is broadened out, light gets in the shadow, and in the lit region, there are some oscillations. He wanted to understand this, and this is why he spoke about a motion like that of an eel. Now, before to show that Newton was right, and this was not the motivation of the work, one had to plot Sommerfeld's solution in the correct way. And this was done by Braunbach and Laukier in 1952. And they plotted what now we call the Madelung trajectories, the integral curves of the Poynting vector, the energy streamlines. And here, I'll show you this in a moment, here's the edge, and here you see Newton's eels. Now, not only that, Newton was extremely brilliant because he said, do not the rays begin to bend before they arrive at the bodies. So I think one can say that in a qualitative way, Newton anticipated Madelung in the sense that Madelung's trajectories are the closest in wave optics or wave physics to the rays of geometrical optics. But Newton did not seem to have contemplated the fact that the force which causes this undulation is strong enough to cause these trajectories to close. And if you look in the reflected region, here they do close, and there are some phase singularities there. See, Newton's force is minus the gradient of the wave potential. So it really is everything he said we understand in modern concept. This was not the reason why Braunbach and Laukier made their calculations, but it's an implication of their calculations that Isaac Newton was right. So we can zoom in. Here are the streamlines, and here's the phase. And if you zoom into one square wavelength, you see these undulations. And they arise actually from destructive interference between three waves: the incident light reflected from the screen and diffracted from the edge. And indeed, if you do asymptotics of the Fresnel integrals, you can approximate, and there are three terms. There's the incident, there's the reflected, and there's this wave. Thomas Young conceived of edge waves. And it's nice asymptotics. These come from saddle point asymptotics of the Fresnel integral, and this comes from endpoint asymptotics. Elementary asymptotics, but still a very good physical illustration explaining something which goes back now nearly 300 years. Okay, now I want to speak about the wave potential and geometrical optics. It might seem that from this connection that the formal limit of short waves, large external wave number, semi-classical, that vanishing wave potential, largely, would correspond to geometrical optics. But that's wrong, because for all non-trivial waves, this density also involves K0 itself. It's a complicated interference structure. And the dependence is usually highly singular. For example, it can represent oscillations. So I want to find the real connection, meaning of the wave potential. Now, just a brief comment about this singular. Geometrical optics is a very singular limit. It's a very long story with many aspects: decoherence, quantum chaos, diffraction catastrophes, divergent series, many connections discussed elsewhere. But the true significance of vanishing wave potential involves superoscillations, and I have to briefly describe them. Another large subject, normally a whole lecture. Superoscillations are functions that vary faster than they should. Band-limited functions, maximum interval of a Fourier variable, conventionally you would think that the fastest variation comes from the extremes of the Fourier integral or sum. But counterintuitively, functions like this can oscillate arbitrarily faster than their fastest Fourier component. Over arbitrary large intervals, they can super oscillate. There's no paradox in this. That's to be discussed elsewhere. But now I want to make the connection with what I've been discussing. One measure of superoscillations is the length of the local wave vector. Now, if you have solutions Helmholtz in free space, they are band limited. They're superpositions of plane waves, all of which have the same length wave number. But superoscillations are where the local wave vector is longer than the wave vector of all the plane waves in the superposition. And this can happen. Here's a superposition of 10 plane waves, for example, with all of which have wavelength 2 pi, wave number 1. The intensity, the zeros are black. There are some zeros here. And here is the phase and the Madelung streamlines. And because the phase varies by 2 pi as you go round, this on an arbitrarily small range, it means the local wave vector is arbitrarily large. It's infinite near at these singularities. So that's one connection. They're places of very large local wave vector. Now, if you just look at the region of superoscillations, that's where the local wave vector is greater than wave vector 1 in all the plane waves, 10 of them in this picture. Of course, it always includes the vortices. Now, you might ask, how big is this region of superoscillations? Well, on the average, for a random wave, 1/3 of the area is superoscillatory. Mark Dennis discovered this, and then together we looked at the similar phenomena in more dimensions. Okay, now what's the connection with the wave potential? Here's again Helmholtz with refractive index 1. You're looking at waves in empty space, but could be complicated superpositions of plane waves. The potential is the wave vector squared of all the waves in the superposition minus the length of the local vector. Well, it's obvious from this that when the potential is 0, when these are equal. And this is the boundary of the region of superoscillation. So that's the meaning of vanishing potential. It's the boundary of the region of superoscillations. And actually, in the superoscillatory regime, the wave potential is negative. Good. Now, this might be thought to be artificial, because if you have a refractive index that varies, the solutions are not band limited, and the concept might seem to be empty. But you can generalize, and Pragya Shukla and I have done that. Local oscillations faster than geometrical optics would allow. In other words, the local oscillations are greater than what you would expect with the potential. It's the analog of quantum counterpart, is that the local wave vector is greater than the square, greater than energy minus the potential. So the classically forbidden region, where the energy is less than the, is always superoscillatory because it's negative and the local wave vector squared is positive. So the concept applies. I want to give you an example. Let the refractive index vary with height, y. These are falling waves. It's as though you have a gravitational field. It's the opposite of what happens in the mirage, where rays bend up. Here they bend down. And the solutions are superpositions of airy functions vertically and plane waves horizontally. And geometrically, one of these corresponds to a family of parabolic rays. Now, let's have a look at the superoscillations, the superposition. That's where the local wave vector length is greater than minus y. So for y greater than 0, it's always superoscillatory. That's a forbidden region. Let's look at this little superposition, 2 of them, one moving upwards and one moving upwards with some horizontal waviness. Well, I've colored the superoscillations. They're colored by argument of the wave, and they result from interference between the classical paths moving up or moving down. You can work that out in great detail. Random falling waves are interesting, very many of them. That's a Gaussian random function. Here's one sample. And again, you see this interference region. You could ask, what's the probability that if you, at a particular height, the wave is superoscillatory? Well, of course, once you're above, probability is 1. of course, because it's all forbidden. But here, more complicated, but it undulation, and the limit when you go deep down, it's as though it's a Gaussian random wave in empty space. It's the 1/3 again. So one understands this in some detail. Now, another point. I've said that the vortices form closed loops. Well, that's a special case. It applies to wave equations of the usual form, and it comes because of this divergence behavior. But in paraxial optics, for example, which is an approximation where one direction is considered fast and you throw away high derivatives, the divergence isn't zero, and the vortices need not form closed loop. And so let me explain. You have a propagation direction y, and then slowly varying x and y. Well, I want to give you an example. An exact solution of the paraxial equation is this Pearcey integral. You just accept that it is. Not an exact solution of Helmholtz, an approximation. It describes diffraction near a geometrically cusped caustic and occurs in many examples of wave optics, including paraxial optics. Many waves, evolving wave patterns from smooth wavefronts have this behavior. Now, it's an exact solution, as I said. Well, let's look at the phase and let's look at the Madelung trajectories. They're not closed. You can see this, that they spiral and they spiral. The spirals are very tight. Here's a vortex. When I looked, before I realized this nice example, 20 years ago, I wrote about, in the generality about this behavior, and typically the spirals are very tight. If you're close to a vortex, then the distance between successive windings, which would be zero if they were closed loops, is of order r³. So they very, very quickly close by become indistinguishable from circles, but they're not. They very slowly spiral in or spiral out. Now, something again different. I mean, this is exploring the different anatomies of waves in the context of this Madelung trajectories. You have the paraxial equation in free space. You multiply by this overall plane wave, and then you've got this approximation. It's first order in the propagation direction and second order elsewhere. Now this represents propagation in, it's like propagation in xy indeed, yes, but the Madelung trajectories are again generated by the phase gradient. But if you replace y by time, then this is the time-dependent Schrödinger equation for a particle moving in one dimension, in x. And then the Madelung trajectories, there's this sideways wave number, and the integral curves in space-time are the Madelung trajectories, and they're completely different. Here's an exact, has a good example, because, and it's an exact solution of Helmholtz as well as the paraxial equation. There are some special cases of that type. So here it is. There are two phase singularities, and here's the wave vector in xy. But in xt, completely different. And one reason is that propagation can't come backwards paraxially. So you can't get these backflowing regions. And here, completely different. And this is a generic behavior of the Madelung trajectories of the time-dependent Schrödinger equation. They avoid the singularity except for one, which encounters it in a cusp. I've recently published a paper describing this in generality. So the same mathematics can have different physical interpretations. We're familiar with that, of course, in other contexts, but here the contexts are rather close. One is time-dependent Schrödinger in one dimension, the other is paraxial in two space dimensions, but the corresponding trajectories are completely different. Good. Now, another subject whose relevance you'll see soon. Newtonian mechanics, first of all, curl forces. Let me talk about them. Now, we're talking about the acceleration. That's what Newtonian mechanics is about. But we're thinking that the force, the acceleration, depends on position but not velocity, but it isn't the gradient of a potential. In other words, in Newtonian mechanics, first of all, particles, the acceleration, the derivative of velocity, is given by the force, but the force is not the gradient of the curl is zero. The force is not the gradient of a potential. Okay. Now, this means generically there's no Hamiltonian or Lagrangians, there's no phase space, but there is a state space, there's position and velocity. And Pragya-Shukla, yes? Pragya-Shukla and I have written a number of papers about this general case of Newtonian mechanics, which is hardly discussed. So the state space is position and velocity, which is a gradient. Now, for example, x, y, x velocity, y velocity. Now, first of all, volume is conserved in this state space. So although the motion is non-conservative, energy is not conserved around a closed loop, there's no dissipation. So it's dissipationless but non-conservative. More significant, Noether's relation between symmetry and conservation laws is broken when you don't have a Hamiltonian or a Lagrangian. There are simple examples, I'll give one in a minute, of symmetries without conservation laws, and you can easily create examples of conservation laws that don't correspond to symmetries. This subject was started in the 1920s. It occurred rather mysteriously in the dynamics of whirling shafts, but now it comes back in that there are optical forces on small absorbing particles, in addition to the force responsible for trapping, which is a gradient force. It's the gradient of the optical intensity, but there's an additional force in the literature, it's called the scattering force, where which is of this non-conservative type. And I just want to say something interesting. It's non-zero if the particles are small and absorbing, but the motion it gives rise to is non-dissipative in phase space. And this is the opposite of what we're familiar with in statistical mechanics, for example, where friction is macroscopic irreversibility arising from microscopic elastic motion, Hamiltonian motion. It's completely different. Here, the microscopic motion is absorbing, but the macroscopic motion is non-dissipative. We've discussed this in detail, and I just mention it now because it's interesting, but it's not part of the main story. We wondered whether, now we come back to our theme, whether these curl forces have a quantum counterpart. Now, we've recently realized that there's a generalization of Madelung, where instead of individual particles, as with Madelung, you have fields, a density field and a velocity field. Madelung, this corresponds to wave. Here it won't. And derived from the Schrödinger equation. Okay. And you do the polar representation. And again, this velocity is the phase gradient. Now, the standard quantum Madelung Newton equation is that the acceleration is the classical force plus the quantum force. I've mentioned that already, gradient of a potential. And you have this quantum potential, and you have continuity. Now, the fields are coupled by this continuity and by the quantum potential. Now, the generalization, again with Pragya-Shukla, is that the acceleration is given by the classical curl force that we've studied already, plus the Madelung quantum force. In other words, you've got rate of change of velocity field, which is the partial derivative of t plus the convective term, is the curl force now, non-curl non-zero, with the quantum potential. So that's a very natural generalization. We preserve the continuity equation, we preserve the quantum potential, but we throw away the phase circulation, and we have to do that for a reason you'll see in a moment. You'll see it now. Look at the vorticity of this potential. Well, the vorticity, if you use as a simple equation, take the cross product of the velocity and the vorticity, and there's a relation between that. And if you take the curl of it, you get that the curl of the force is, which is non-zero now, is a quantity that involves only the vorticity here. And so if the vorticity is zero, you can't have a curl force. So quantum curl force trajectories have non-zero vorticity, and so they're not the gradient of a phase as in our model. Now, you can think of 4 levels of dynamics. Newtonian conservative dynamics, force is minus the phase gradient. There's no quantum potential. It's classical. Newtonian curl force, quantum potential is zero, but now the force isn't derivable from a potential. Madelung quantum, you don't have a quantum potential. Excuse me, you do have a quantum potential, but the force is curl free. It's a gradient of potential. And finally, our level, quantum curl, the curl is non-zero and the quantum potential is non-zero. Now, it's extraordinarily difficult to solve these coupled equations for a general quantum curl force. We are thinking about that now. But I'll give you an example in a moment where you can do it. We're interested, for simplicity, in stationary fields where they're still non-linearly coupled. Now, the continuity equation says that the current is divergenceless and there's no partial derivative with respect to time, but still there's the convective time acceleration, and that's equal to the force minus the gradient of the quantum potential. Okay, so this is the formalism. Now, here's a solvable special case, which is extraordinarily subtle, and it's only marginally curly. Consider this force, circulating force, inversely proportional to distance. Well, this force has the form of an ideal irrotational vortex, but it's not completely curl-free because there's a delta function. There's curl at the origin, as there must be from Stokes' singularity theorem. So provided you keep away from the origin, you can think in Hamiltonian terms. And here it is. You cut out the position here, and then the force is the gradient of potential, but the potential is not single valued. It's minus theta. So the domain is not the plane, but the full line, including windings. Now, there is a Hamiltonian. Here it is. Looks very simple. Time-dependent Hamiltonian. There it is. It's single valued on the helicoid, but not on the plane. But you can make a gauge transformation, time-dependent gauge transformation, which eliminates this potential theta and restores single valuedness in the plane now. And what it is, I don't want to go through all this detail, just look at this. It's the Aharonov-Bohm dynamics. It's as though there's a magnetic flux line at the singular point, whose strength is increasing with time. That's not the normal Aharonov-Bohm. Normal Aharonov-Bohm has a fixed strength. It's somewhat related to motion in a cyclotron, but it's a simple version of that. Okay, now this is separable in r and theta. You pay a price. You have explicit time involved now, but so you can superpose plane waves, or circular waves in theta, single valued wave functions, times a radial equation, which now depends on time. And here's the time-dependent radial equation. Okay, so the question is, what does this all look like? Well, first thing, the canonical angular momentum, the phase gradient, is a multiple of Planck's constant. Very good. Now, however, the canonical angular momentum is not the same as the gauge invariant kinetic angular momentum, the one which corresponds to r cross v velocity, not r cross momentum. And this is mh bar plus t. So it's increasing, and indeed it must be, because this is a force which is rotational, and so of course it will increase the angular momentum. It is, however, circularly symmetric, so it's an example of non-Noether. There's circular symmetry, this azimuthal torque but the angular momentum is increasing. Well, let's look at the classical orbits. We showed a number of years ago. It's non-trivial. They wind very slowly. The radius increases a bit faster than linearly. The angle increases as the square root of the logarithm of t. So very slowly you get a trajectory where it comes, let's say, from near the origin, very slowly rotates. Just to give you an example, the nth winding is a time exponential of 4 pi squared n squared. So a time 10 to the 15 for the first winding, is why you don't see it here, 10 to the 66 for the second winding, 10 to the 151 for the next winding. Now, quantum states don't correspond to individual trajectories. We want to consider quantum states corresponding to families. And it's simple to consider a family with a single winding, and you have, this is the radial wave equation, and you choose an initial state concentrating near a particular radius. Here it is, a little ring concentrated. It's convenient to put the Planck's constant here, because then the momentum distribution, the strength of it, is classical, right, with pi. Very good. Now, let's have a look. Here are some classical trajectories. You can't see them clearly. You see a Moiré pattern, but there's a caustic here. If you magnify, you can see that the trajectories just go down and come up. So there are pairs. You get interference in here. Quantum, you can't see the details, but you can see something to do with interference is that the Madelung trajectories, which are all hidden away in these red regions, they're in bands, and there are bands which are avoided. If you look in detail, you zoom in, you again see Newton's eels, these undulations that were emphasized in the Madelung picture. They're the representation of interference. Now, there's quite a lot of calculation behind what I've shown you, and it's very easy to make mistakes. So a very good test is the semi-classical approximation. So here's the quantum, and I'm looking along here at the wave. So here's the exact wave, which is red, and here's the caustic down here. You have the classic airy behavior. Here's a semi-classical. I didn't bother to include the airy, so it diverges, but elsewhere it fits perfectly. And you have to include everything, the correct phase, the action along the trajectory, and so on. And here you zoom in, and it's absolutely almost perfect agreement. So we know we didn't make mistakes. And this is just dipping the toe into this vast field of unexplored field of quantum curl forces. Now, I want to finish with something which is work that I'm actually doing now and haven't yet published. It's interesting to consider, for reasons I'll tell you in a minute, Hamiltonians where the kinetic energy is anisotropic. The simplest case is a free particle. That's what I'm going to talk about. So here's the Schrödinger equation. There are examples, for example, hyperbolic optical metamaterials, where one of the principal components of the dielectric tensor is negative. Anisotropic electron mass in solids, the effective mass, I should say. But the reason we are studying this is that there's a special class, a very restricted class of curl forces for which the acceleration is not the gradient potential, but because the Hamiltonian is anisotropic, this does give rise to an acceleration, as I say, which is of the type which is curly. That's if you add a potential here. And another is that this equation is actually the Klein-Gordon equation if you replace x by time. So we'll come to that in a little while. So it's worth looking at this, what seems to be a ridiculously simple equation. Now, however, it's enormously different from the very, very familiar isotropic kinetic energy, which describes waves in empty space. So the plane waves, for example, are solutions, but the dispersion relation is different. It's kx squared minus ky squared equals 2e. So the constant energy curves in momentum space are hyperbolas. These 3 points will correspond to a superposition I will show you in a little while, 3 plane waves. But they're different plane waves, different points on the same energy curve can have very different wave numbers, because kx squared plus ky squared is not constant along the energy curves. It's kx squared minus ky squared, which is. Well, again, Madelung, canonical momentum, but now the velocity streamlines require the kinetic momentum. It's another version of the difference between wave velocity, phase velocity, and group velocity. Now, from the first Hamilton equation, velocity is px minus py. So the natural generalization is you take the gradient of phase in the x direction minus the gradient of phase in the y direction. And to confirm this interpretation, if you do Madelung for anisotropic, kinetically anisotropic Hamiltonian, which I didn't see in the literature, it involves the v, not the u. So the continuity equation involves the kinetic momentum, the velocity, and not the canonical. And the corresponding Newton equation, velocity of particles, is the derivative of velocity, and that's equal to something involving this modified quantum potential, which is again anisotropic. So Madelung naturally involves the v, not the u. We need to think about it. And the streamlines of the v and the u are fundamentally different, and they're fundamentally different, especially near these special places where the phase is singular, or where the phase has a critical point, its station has a saddle point, gradient of phase is zero. And I want to illustrate that. We've seen that near phase singularities, the canonical streamlines are circles, optical vortices. I didn't emphasize it, but it was shown in the pictures that near phase saddles, the canonical streamlines are hyperbolas. It's the opposite for the V streamlines. They're hyperbolas near the phase singularities, and they're ellipses near the phase singularities. So the index of these singularities is reversed of these streamlines. And here's an example. This is an exact solution of the anisotropic free particle equation. And it has phase vortices at plus or minus along the y-axis, plus or minus a half, and also phase saddles a little bit farther away. So here is the phase. It's color-coded again. And here are the canonical streamlines. As I've shown you before, circles around the phase singularities and hyperbolas around the phase saddles. But the kinetic is completely different. Hyperbolas near the phase singularities, and closed loop actually ellipses in general near the saddle points. And here you see them both together, the canonical and the kinetic. It's a very interesting, and to me it was unexpected. It's obvious once you think about it, but to my knowledge, people had always thought that phase singularities must correspond to circular streamlines. No, not the case. By the way, since we're discussing critical points of phase, what about phase minima and phase maxima? Well, you can show that for a kinetically isotropic Hamiltonian, there are no phase extrema, no phase maxima or minima. There's no such restriction for the anisotropic Hamiltonians. And so I wondered, where are the phase maxima and minima? They are very rare. I don't have a general theory, but I searched a number of examples. I had to superpose 5 plane waves with different phases and different intensities. And then finally, I found a region where very, very shallow phase maximum and a phase minimum. So they're rare. There are other aspects of wave singularity theory where there are similar, rather rare singular phenomena. I won't go into that, but understanding this goes back at least almost 50 years now, when I worked with John Hannay when he first came to Bristol. So it's just a small part of the story. A difficult statistical calculation for plane waves, but for random waves, will be what's the probability if you choose a point and find that it's a place where the phase is stationary, what's the probability that actually it's a maximum or a minimum? And the answer, it would be a small number. I don't know what it is. Just let me show you an example. There's 3 plane waves with all with the same energy. Okay, so this is monochromatic. And here's the canonical, and here's the kinetic. And I've superposed on the intensity. So there are zeros, phase singularities, phase saddles. Here again, you have phase singularity. Just a second. Yes, here's a phase singularity, and you have a saddle point. Excuse me, you have hyperbolic trajectories, and here's a phase saddle where you have circulating trajectories. What I've drawn here is the mean kinetic average momentum that you would get if these were geometrical plane waves and you didn't have interference. Again, here's the canonical, here's the kinetic. I've now superimposed them on the phase pattern, but it's otherwise the same as before. And the very last thing I want to tell you is the following. Of course, general solutions are superpositions of plane waves. And in the familiar case, which is the case of isotropic, there's a very simple superposition of plane waves, which are just these Bessel waves, the first of a whole hierarchy of angular momentum waves. This is the angular momentum 0. And if you have the isotropic Hamiltonian, you have ordinary plane waves, x cos theta plus y sine theta, superpose them, traveling in all directions, and you get this J0. Now, there's a simple anisotropic counterpart. Y goes to Iy, and this would be a Bessel function of x squared minus y squared. Now, this is an unacceptable solution because when y is greater than x, this is a Bessel function of the imaginary argument, which is the Bessel function I of the second kind, which grows exponentially in the y-axis. So this is unacceptable as a solution. So we need to think more carefully. Here's a superposition, a discrete superposition of plane waves which do satisfy the anisotropic wave equation. Kx squared minus ky squared is a constant, 1 in this case. Superposing lots of them, this n delta is the analog of the direction of the plane waves that give you the Bessel. Well, when you calculate it, you get something very surprising. You get some oscillations, Bessel function expected, but here in the bad region where things would diverge, it's as though the intensity is a constant. Actually, the constant is 0, you'll see in a moment. Well, the continuous counterpart of this is an integral. Here it is. And this integral is actually known. It's you can analytically calculate it. I won't go into details. It is indeed a Bessel function, but the bad region is forbidden, and it's also an odd function. Well, compute it. Here it is, 0 Bessel function minus Bessel, because this is an odd function. And if you, just to really convince yourself, if you take a section along here, here it is, and calculate black dashed this function, here it is, oscillatory, 0 in between in this region, but then compare it with a discrete superposition that I showed you, and you see it's a kind of Gibbs phenomenon, but it basically reproduces what this continuous limit gives. Now, it's a puzzle, it's a surprising thing because, you know, you've got 2 solutions. One is just J0, smooth, unacceptable. The other is this solution with a step function. But if you put you might think this might spoil a solution, this step function. Well, you can calculate the discrepancy, calculate the deviation from solutions of the equation, and it's some combination of delta functions and derivatives of delta functions, which you can show is actually 0. So in other words, this doesn't spoil the solution. So it's kind of remarkable that you've got this discontinuous, you can call it an eigenfunction. It's, of course, a continuous spectrum, so it's not a bound state, not square integrable. Now, you can demystify by writing the Klein-Gordon equation, which is exactly the same as the anisotropic equation, and the energy corresponds to mass squared. Then this solution is a causal solution. It's zero outside the light cone. So everything behaves as it should. And with this space-time interpretation, it seems natural. Now, conclusion. These Madelung trajectories, they enable alternative understandings of familiar phenomena, connections between several concepts, and suggest generalizations. You know, velocity streamlines, undulations representing interference, Newton's eels, wave vortices, superoscillations, the meaning of the vanishing quantum potential, generalized superoscillations when you don't have band-limited functions, paraxial streamlines need not close, classical and quantum curl forces in progress, and kinetically anisotropic Hamiltonians. And connections are actually very important in physics. And I want to quote a very wise statement of my former very distinguished colleague, Charles Frank. Physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. And there are a number of papers on these matters, but I will stop here. I thank you very much for your attention, and I have kept within the hour. Good.
Thank you very much for this wonderful presentation and demonstration of the beauty of physics. So we have already raised hands, and
Shall I stop sharing my screen so I can see?
It depends on the questions. Yeah.
Well,
Maybe
okay.
someone asked about questions about.
Well, let me see. Okay. Good.
Let us start with Dennis Bonder.
Yes.
Please, Dennis.
Good morning from New Orleans. Nice to see you, my Professor Berry, again. And actually, I wanted to say that when Professor Berry mentioned that if you have questions, you can email him. I can assure you from my personal experience, that's really what happens. He replies very quickly and very thoroughly.
Well, let's see.
So, but that's not an endorsement to send 100 emails to Professor Berry, obviously. I wanted to ask a question. You mentioned this very interesting phenomenon of macroscopic reversibility by microscopic irreversibility. You promised to come back to it, but you did not come back.
No, I didn't promise. I said we discussed it in some detail in the paper. I can't.
Okay. I would be
Anyway.
interested to see that paper, actually, if you could pull out the reference or maybe put it in the chat, would be great. And second question, there is a Yonta Kobayashi angle for Dirac equation, which characterizes like composition of positive and negative solutions of Dirac. Is it related in some sense? Because I see the Kobayashi obviously appearing here.
Yes, Takahashi, very wise papers from him in the 1950s, and they're at last getting the attention they deserve. But yes, I didn't think of the directly in this context, but there are other connections with super oscillations. In this sense, you can define a local velocity, and if you superpose solution of the Dirac equation, which are all subluminal, the local group velocity, which is the counterpart of what I've been discussing, can be superluminal. So locally, you can have superluminal propagation. And I've written about this for the Klein-Gordon and the Dirac equations. And statistically, you can calculate the probability of these superoscillatory regions or superluminal regions where the local group velocity is greater or less than greater than the speed of light or minus it. And you know, if you plot out regions in space-time where you choose a superposition of a number of plane Dirac or Klein-Gordon waves, then there are curiously shaped regions whose topology I don't understand, where the local velocity is superluminal. So that's the best answer I can give to your question. It's sort of related, but I didn't look at the corresponding streamlines. Yes, good.
So we have a question from Gleb Skorobogatko, please.
Okay. First of all, thank you very much for this very interesting talk. And my question is following. So from your talk is obvious that there are many interesting and sometimes hidden interconnections between classical picture of interference in nonlinear optic on the mathematical level and the quantum mechanical description, which is also involves very strongly interference phenomenon. And for me, it seems that in some of aspect of your subject points of classical phase singularity can be treated as a point of strong phase fluctuations. And we know that the key point for quantum mechanics is strong quantum fluctuations. But also another important thing about quantum phenomena is that it's such phenomena are non-local. So different points in space which experience quantum fluctuation can be connected to each other via quantum tunneling and so on. And it's very interesting whether on this classical but very non-linear, very complicated level, such points of strong phase fluctuations or phase singularity can feel each other or not. So can these points of phase singularity feel somehow each other due to the flows which
it's very interesting. They tend to repel each other for topological reasons to do with index, and they're associated with saddles. So an example, something discovered by my colleagues some years ago, is people consider reactions between. You can have a positive circulation and a negative come together and cancelling each other, giving nothing. But this must be accompanied by saddle points for reasons of index. Total index has to be conserved, and there are different topological conserved quantities. And this means that the singularities tend to repel each other. In linear wave theory, which is what I was discussing, the classical motion could be non-linear, but the waves are in linear motion. The phase singularities have some resemblance to dislocations in crystals, and there's a strong kinematic analogy, but there isn't a dynamical analogy. It's hard to, you don't think of forces between these singularities. For nonlinear optics, there is something of this, but for linear, not. So there's a kinematic, but not dynamical. But they have interesting physical effects, and I will tell you one. Imagine that you have an optical field where you have some phase singularities, monochromatic. So all the momenta in the plane waves have the same value, but locally you can have very fast, very large phase local momentum. Now you put quantum particles, for example, a two-state atom, coupling with dipole coupling, let's say, to that field. Now the atom will experience a force, of course. It will experience a force, and the force you can show depends on the local momentum. So the atom can acquire kicks in the field. This is a paper with Stephen Barnett. And these kicks, apparently paradoxical, can be much greater and much stronger than any of the momenta in the plane waves that make up the field. Now, this sounds paradoxical, but it isn't, because these kicks, large kicks, take place near the vortex where the intensity is very low. So they're very improbable, they're rare. So you have this phenomenon of large but very rare, but we call them super kicks. Now, to demystify this, you ask, what is the average? Well, it's just radiation pressure. if you take radiation pressure and look microscopically near a wave where the intensity is varying and there are zeros, not the usual plane wave that one considers, then radiation pressure deconstructs there into extremely large, extremely rare kicks. So, but on the average, it's what you would expect on the basis of the average of the Poynting vector. So there are influences and there are connections. I would like to see experiments. I've proposed some on to see these super kicks, these very rare. So this is one example of a physical effect of one of these phase singularities. There are others, but just
Thank
one
you.
response to your question. Thank you very much
Okay.
for it.
Thank you.
Yeah, good.
The next question from Mikola Bondarenko.
Thank you. And thank you very much for a broad overview of the new phenomenon. I had two questions. First, well, if I dare put it more broadly, well, in more physical terms, is it fair to say that those phenomena like Newton's eel and superoscillations are just like acoustics, anyway, due to the property of waves to sense the areas neighboring to the area that you consider, unlike the point-like particles? So this is just basically the same reasons, but more spectacular phenomena.
Yes. Thank you very much for this question. It gives me the chance to say something which I didn't have time to say. Caustics and phase singularities are complementary to each other in this sense. Caustics appear as singularities in families of waves, in families of rays, in geometrical optics. Wave optics smooth them out, but you can still see them very strongly, decorated with area functions and piercing functions, whatever. But still, they're basically geometrical optical phenomena. Phase singularities are essentially wave phenomena. They result from extreme destructive interference. To see a phase singularity, you have to be looking on the wavelength or sub-wavelength scale. On that scale, caustics are big, smoothed out things, smoothed out by diffraction. To see a caustic, you have to look from far away and where the wavelength is negligible, and this blurs away all of the phase singularities. So we're talking about two complementary regimes, one of which in geometrical optics, the intensity will be infinite, the other in wave optics, where the intensity will be zero. So yes, they are conceptually related in the sense of being singularities, but they have very different structures, and they occur, in a sense, in opposite regimes.
Thank you very much. And I have another question, please. Well,
yes.
If this quantum potential embodies everything which is related and responsible for quantum effects, it must cause not only oscillations but also diffusion or spread of the spread of wave packets. So is there any trace of wave spreading in the problems that you study, or maybe the oscillations?
Well, yes, it would be wave spreading if I were to look at fairly localized waves. I didn't want to do that. I wanted to look at waves that occupy a large regime and look at the details of the structure inside. But if you have a Gaussian beam in paraxial optics, then there's no interference. It's a family of sort of hyperbolic trajectories where, again, you can think of the trajectories as being the result of the quantum potential. You don't get zeros there because you don't have interference, but you get the analog, which is I mentioned these undulations. Well, the simplest type of undulation is just a curve. And so in a Gaussian beam, the phase gradient is curved. I have a paper with sorry, I'm forgetting stupidly the name, contrasting the geometrical trajectories and the phase gradient integral curves for Laguerre-Gauss beams, where you have circulation, different angular momenta. And then the classical trajectories are families of straight lines which are oblique, and there's a caustic. They have envelopes, and they behave approximately conically. But individual straight lines are straight, but they assemble into a pattern that circulates. Whereas the corresponding quantum or wave optics Poynting vector things, they really do wind helically. And so we studied this in some detail about 10 years ago. So the answer is yeah, and the spreading is part of that story.
I was asking actually because actually spreading effects are usually bigger than oscillatory ones.
Yes.
Kind of not exponentially suppressed by a power law like this.
Yes, I didn't think about it, but I'm pretty sure that if you take a Gaussian beam, you can think of the spreading as being an effect of the quantum potential. I didn't look at it that way, although I expect people have. So you mentioned the quantum potential, what effects it has, but I think the phase singularities are more interesting because they're sort of topological features. But you're right, the spreading is there, and you can probably account for it within this framework, thinking of the quantum potential.
Thank you very much.
I didn't do it.
We have a question from Konstantin Bilov.
Kostya, hello, how are you?
Hello, Michael. Very good, and I'm glad to hear you. And fascinating talk as always.
And although your home is Kharkiv, you're not there now, right?
No, only our signals meet in Kharkiv, unfortunately.
Yes. Where are you, by the way?
I'm in February 7th in Tokyo because it's already February 7th in Tokyo.
Oh, in Tokyo, right? Okay.
Yeah. So I have the half remark, half question for you concerning the last slides you showed about this hyperbolic-like solution with theta function, right?
Yes.
And this reminded me problem I considered about 6 years ago. So you started with the Bessel functions, which are eigenmodes of N-Gor momentum operator.
Indeed.
And then you end up with something which looks like hyperbolic solution. And what I analyzed, I tried to find eigenmodes of the Lorentz boost operator for which look very similar to what you found.
Well, yes, because they would probably solve the Klein-Gordon equation.
Exactly, yes.
Yes,
so
very good.
I think that there is not it's natural relation. So you start instead of elliptical geometry, you come to hyperbolic geometry.
But the unexpected feature is that you have this cutoff. You have this singular boundary.
Absolutely.
That's the feature. That's what surprised. That's what was, and it's as you obviously understand, in the relativistic case, this represents causality.
Absolutely,
it's not so mysterious anymore.
Yeah, I found the same type of solution with theta function with this cutoff, and then on analytical.
Send me your paper.
Sure, I will.
Please.
So I thought it's a nice connection.
Good, thank you.
Thank you.
Good. Yeah.
Great. So we have a question from Yaroslav. Yaroslav, please unmute yourself.
Thank you. So it's a less highbrow, more clarification question. Naively, in my mind, what you say is, okay, on a very general level, you have a wave equation, and then you have some kind of hydrodynamic equation. There is some kind of equivalence. You can study it from both sides.
Yes.
And my question is, so it's kind of clear when you talk about one particle in if you think about quantum mechanics and you say, okay, we have one particle and wave equation for it, is it possible to think this way about multiple particles? Is that useful?
It's a very good question. I haven't studied it, and obviously you can. I mean, there will be a Madelung version, but I didn't think about it. I'm sure people have, but not me. So it's the quick answer is I don't know what the details will be like. I mean, one of the reasons for, let me just say, I mean, from one point of view, single particle problems are kind of trivial. But where they're not trivial is you ask for details and topology and geometry of the waves when you have many superposed waves. Many body versions of this will be another dimension entirely. You know, in quantum chaos, people talk now about many body quantum chaos, many body localization as the beginning of this extension. But I haven't studied it, so I can't give you an answer. I can't give you an answer.
Thank you.
Yeah, sorry. Yeah.
We have a question from Konstantin Vukin.
Thank you. I have two short questions. Of course, first of all, excellent presentation, very informative, but also generates questions. So very technical question. The interference of three waves. What was the restriction, or what you consider the ratio? Which ratio you took between K1, K2, and K3?
Say it again. I don't hear I can't hear you well. Say it again.
I'm curious in the example of the interference of three waves. What was the ratio between K1, K2, and K3?
Oh, quite big. Factor of 11 or so, 10 or 11.
So even for so large difference, you have this interference.
Yeah, because I chose two of them rather close to that boundary in K space, rather close to those crossing. So the energy curves are hyperbolas, and near the diagonals of near the crossing, x squared equals y squared. The discrepancy of the x and y components is very large.
Okay. Thank you. The second question related, when you showed us, I did not memorize which problem was considered, but you mentioned difference between superpositional in the classical case and quantum case. And surprise for me was the quantum case, the beams, the spreading beams looks completely isolated. But when we took the finite, not integral, but the summation, the series.
Yes.
But you know that in the quantum carpets in the box, that's completely different picture.
Yes.
Multiple. So what is the reason why they are isolated, not superimposed?
Because I mean we're not speaking about eigenmodes in enclosure. These are real functions, and the nodes have codimension 1. They're lines in 2 dimensions. But with the complex waves that you have when you have propagation, then they're codimension 2, because the real part and the imaginary part must be. And that's the case I was speaking about, which is in a sense generic. So one way to express it, we emphasize this drawn nigh, and when 50 years ago this year we wrote our paper on the phase singularities. They're the generalization of what in classical optics people used to call the dark interference fringes. People thought of them as surfaces. Well, they're not. In 3 dimensions, they're lines. In 2 dimensions, they're points. And it's only very special cases where they're surfaces in 3 dimensions. And so we were emphasizing that we were considering the generic structures that are stable under perturbation. And for propagating waves, these have codimension 2, not codimension 1.
Okay, this was something different representation. I just wanted to mention that many years ago, I suggested to analyze the evolution of the wave packet in box, producing quantum carpets, pictures.
Yes.
Okay? But I suggested use not eigenvalues, but the free space propagator with reflect bouncing from the border, the boundary condition. And in the finite increasing number of bouncings, the solution coincides with the traditional approach when taking eigenvalues.
Yes, right. Simple. Yes.
Yeah, but this allows us to split the diffusion and propagation processes. Then I analyzed. Then I thought you did the same. And okay. Anyway, thank you for.
Yeah, no, it's very interesting. I mean, I looked at these waves. I mean, there are all kinds of connections in the time-dependent Schrödinger equation. These give you quantum revivals, as they're called. But in optics, it's the old Talbot effect, which is the same. It's like a plane wave beyond a diffraction grating. You get repetitions, and we found that it was known, of course, that if you have rational fractions of the repetition distance, you get more complicated superpositions. And we found that if you have an irrational distance, you get fractals. And we studied this in great detail in the 1990s with Susanna Klein. So yes, I like very much these quantum carpets, like you say. Yeah. Thank you for mentioning.
No,
yes.
I know your contribution. The excellent contribution to these papers.
Yeah. Thank you.
Thank you very much. Thank you.
Good. Yeah. Good.
Next question from Igor Sukrenko.
Yeah, thank you very much for the fascinating talk. My question is pretty naive, but still, so if we consider Bloch waves in a crystal,
yes,
all the restrictions associated to their periodic potential,
yes,
do these conclusions still apply, or are there any special or interesting consequences that arise in such a case?
Well, of course, you know that there are. I mean, there's not what I discussed today, but there's all kinds of things related to geometric phases and curvature and Chern classes and so on, which are degeneracies of the Bloch, but within the Brillouin zone. And there's this huge area of condensed matter physics, which is based on that. But if you would want to see, and of course, the waves can have zeros. I don't know if they've been studied in great detail, but they can have. And certainly you can get caustics. I mean, many decades ago, there was a discussion among electron microscopists who were studying electrons from external electrons going through solids. And of course, you have Bloch waves, superpositions of Bloch waves there. And the question was, when the energy of the electron microscope gets very large, there are two conflicting pictures. One is the potential is very weak, so it would be perturbation, a bit like X-ray diffraction. You use the Born approximation, etc. The other is the wavelength is very small, so you'd get classical mechanics, and the electrons would wind their way through the potential. And what I found, this was more than 50 years ago now, was that a very detailed analysis of these external electron microscope electrons passing through crystalline solids was that actually it's the second case that wins. Eventually, the motion becomes classical, and the reason is that as the energy of the electrons is greater, the first effect of relativity is to make the effective mass of the electrons increase. And so this makes the potential stronger. So that it's 2 mass times potential on h bar squared. So the mass getting bigger is like h bar getting smaller. So eventually it becomes semi-classical, and the limit will be like the limit of classical particle channeling. So that's an answer I can give you. I haven't thought about it for many decades. But the question of, for example, phase singularities in waves inside crystals is very interesting. There must be a literature, but it's not something I've thought about.
Thank you very much.
Thank you, Igor. If there are questions, please raise your hand. I just would like to ask one question.
Yes.
You mentioned kinetic anisotropic Hamiltonians, and
yes.
I wonder, could you maybe name some systems you have in mind where this can be realized?
Well, the systems we were thinking of is that there's a class of curl forces, a very special class that can be represented by Hamiltonians, and this was our reason for looking. But the Hamiltonians that generate accelerations that are not the gradients of potentials are always kinetically anisotropic. But of course, there are applications. I mean, there's a large body of work on these hyperbolic metamaterials where the dispersion relation it involves, for polarization optics, the dispersion relation involves dielectric tensor whose principal components don't all have the same sign. And there are experiments on this because you can make metamaterials which have this problem. I don't know if they occur naturally. They probably do somewhere, but mainly the literature concerns these artificial metamaterials. And people create these, and instead of conical refraction, you have the hyperbolic counterpart. So this is an area extensively explored. In solid state physics, in condensed matter physics, the electrons have an effective mass to do with whether the dispersion of bend up or bend down, and of course this occurs for holes rather than electrons. But the point is that such moves can be anisotropic in different directions, and you could have effective masses which are positive in one direction, negative in others. There's probably quite a large literature which I don't know, but that's a major area of condensed matter physics: electron effective masses inside crystals, which determines, for example, the motion of big electron wave particles, where you need only the Bloch dispersion relation. You don't need the details of the Bloch waves.
Thank you for a complete answer. Yeah, so I do not see raised hands. I assume that scientific questions are over, but I suggest that we stop recording and turn to informal parts. So on behalf of all participants, let me thank you very much for wonderful presentation and wonderful discussion. So we enjoyed
it's really
it
been
very
a
much.
pleasure. And as I said, I'm only sorry that I can't be with you in person. I hope that one day this will be possible in happier times.
Yes, thank you. Yeah. So I stopped recording, and if we have some comments or informal just remarks, please.
If we don't, I will soon leave. But let's be here for just a moment. Yeah.
Yeah, just to give opportunity for guests who are hesitating, maybe say something in scientific part. So please, Gleb, I see the raised hand.
I hesitate because it's second my question. So,
yes.
But it's physical question. You mentioned the systems where you cannot attribute a Hamiltonian to the system, and the system where the Noether theorem
doesn't apply.
Doesn't apply. How this connected with boundary condition in such case?
I don't know that it is. I mean, okay, there are two things. The main work on these curve forces is classical. The quantum version we're still thinking about now. But classically, well, you can have a region which is bounded, where inside the forces are curled forces, and you can have a boundary with a reflection. I think it doesn't make much difference. One phenomenon that I didn't mention because the talk was not primarily about curled forces. One phenomenon is to do with chaos. Now, because there's no Hamiltonian, energy is not conserved. Sometimes other things are conserved, and they're conserved for particular cases, but it's not hard to devise curled forces for which nothing is conserved. Now, that's something unexpected. Now, I'll explain why. You see, suppose you have a system in the plane, 2 degrees of freedom. The state space, not phase, there isn't. The state space is 4-dimensional. Now, in ordinary familiar mechanics, at least energy is conserved, so any chaos is on the energy surface. But we find cases where numerically 4-dimensional regions in the whole phase space are explored chaotically. And this is a very powerful indication that there's a curl force with no underlying Hamiltonian. Because imagine there is a Hamiltonian, but you just can't find it. It's complicated. Then if you would plot, and we have a way of generalization of the Poincare section, if you plot, you would see that the trajectories are restricted to surfaces in this state space. But we don't see that. There are cases where we can see essentially a different kind of chaos. You see, one is familiar in dissipative systems where the forces are velocity dependent. When you get strange attractors and all of that. These are dissipative systems, and the area in state space is not conserved. That's different. Here, the area is conserved. So you have non-dissipative cases where nothing seems to be conserved. And I think that's interesting. Nobody seemed to have taken it up. We wrote about it a few years ago and gave examples. But so these are systems where as long as we did the calculations, the motion, some of the trajectories escape, but some of them in a region explore and don't seem to ever escape. And so it's as though you have boundary conditions, but there aren't any. There are no boundaries. So it's the analog of a bound system, but where you don't have a potential. We don't understand this. We observe it. We noted it. We wrote about it. So
I can explain why I'm asking, just because
yes, please.
when one derives conservation laws using Newton's theorem, there are always surface terms which are supposed to vanish. But if you have not zeros for your function of interest on the boundary, then maybe this is the reason why.
Okay, very interesting. Yeah, I mean, it doesn't directly apply because, as I say, we don't have Noether's theorem, but still, it's the boundary conditions. You're thinking of Noether's theorem in quantum mechanics. We have waves. And we, in the conjectured generalization, which was only recently published, we have the fields, the velocity field and the density field and the quantum potential, but we don't have a wave underlying. So I don't know what the counterpart will be, if there is any. Yeah. Good. So interesting, but I can't make it.
Thank you very much.
Good, thank you.
Please, Professor Lukin, maybe short question or remark.
Just informal question, in general, a little bit provocative. What do you think? Why Schrödinger equation is very successful in using description of real world and being Hamiltonian?
Yeah, good question. I mean, I don't know the answer. I mean, fundamental physics as we know it now. Okay, so the point we make, let me say it clearly. These curl forces is fundamental mechanics in the sense that it's more general. Newtonian mechanics is more general than Hamiltonian because it includes these curl force possibilities. But it's not fundamental physics in the sense that at the fundamental level, everything we know is Hamiltonian. And the answer is I don't know why. And by the way, since we're being provocative, there is something else that what was it? People think the Schrödinger equation is very effective. And people often say, well, it describes all matter, right? Well, it doesn't, we know, because one property of matter with which we are intimately familiar is that some matter is alive. And we don't know where aliveness is in quantum mechanics. We believe it must be there. There's nothing mysterious in addition. But this is not quantum biology. That's a subject where particular biological phenomena are studied with like photosynthesis, the aim being to understand whether they exist because of quantum mechanics or whether quantum mechanics enhances or inhibits them. That's a very active subject. It's good. But I'm thinking of life itself. Where is aliveness in the Schrödinger equation for many particles, maybe plus decoherence, maybe not, I don't know. So when you say the Schrödinger equation is very successful, of course it is, but it also fails in a very, very important area, property of matter.
You mentioned that Schrödinger equation is more general than Newton equation, but I'll tell you, if you postulate existing of quantum potential,
Yes.
the boundary, yes, and fluctuating force, potential fluctuating force, like 0
Yes,
point fluctuations, then introducing the psi function in the phase using the action or a point
yes,
like, then I can derive Schrödinger equation for the case when quantum potential perfectly compensate action of fluctuating force. Then I derive for psi function the Schrödinger equation. And that is why it is conservative, because fluctuation is compensated. Of course, this is another model, another speculation. But again, if you are interested in, I can send you the paper.
Please do. Please do. Yes, yes, do.
Okay, ask
because I'm just, I'll tell you what, you see, for many decades, people didn't speak about Madelung's paper.
Oh,
they
yeah.
spoke about Bohm and de Broglie, and this was all concerned with interpretations, which I consider this misty philosophical, so what is real, what is not real, and so on. But now there's a revival of interest in the Madelung equation as a picture, a way of thinking about ordinary quantum mechanics, and as with all the different pictures, the Wigner phase space picture, non-commuting operators, Hilbert space states, path integrals, each of these different ways gives you different insights. And I think that the Madelung is another such. And it's interesting that coincidentally with my own interest in it, which came from never mind where, there are a lot of people writing about Madelung now. It's an interesting sociological phenomenon in our subject.
Yeah, another insight. You reminded me, once I've seen George Loshak. You know, George Loshak is de Broglie's former student, and he is biographist.
Sorry, which person?
George Loshak.
Oh, he was my friend. He was a very good friend.
Yes.
He came to my house, and I went to his meetings, and I'm friendly with his son, Pierre, mathematician. Yes, George Loshak. Yes.
No, but what happened? I visited his Louis de Broglie Center office in Paris.
Yes.
And we talked each other discussing the quantum mechanics, and I mentioned that with my colleagues we're trying to develop another alternative version of interpretation of quantum mechanics, and more or less what I mentioned here right now. And then he was listening to me very carefully. And then he said, I wish you success. With him, and he pointed on the portrait of de Broglie, we spent 25 years trying to construct the theory of hydrogen atom with our approach, and we failed. But I wish you success. This is another insight. Loshak said that they failed. I didn't know the details. Yeah, I didn't ask. But for me, it's amazing statement. That that this approach, the Bohr and the Schrödinger efficient. That's why this puzzle for me.
Yes. Yeah. By the way, you can have phase singularities in the wave functions in the hydrogen atom. There were papers by Georg Ries in the 1970s actually mentioning this, and I've created superpositions of degenerate states. You need up to about the 6th level degenerate states in the hydrogen atom where the phase singularities are knotted. Okay, interesting topological structure. So the hydrogen atom has many secrets still to reveal, even in elementary quantum mechanics. Yeah. So thank you for mentioning this, and for mentioning George Loshak. Yes.
Loshak, yeah, it's amazing person.
Professor Berry, would you allow for 2 more questions, or
No, just then I must go. Yeah.
yeah,
Yes.
yeah, just one question from Dennis or Bondar.
Thank you. Actually, I want to make a comment about bounds. It's to Gleb that actually, in fact, these things, when you have boundary conditions in physics, also make
Yes.
very interesting effects in classical physics as well.
Yes.
For example, we had a paper not so far a while ago showing that entropy is not conserved for classical Hamiltonian systems. Actually, if you have boundary conditions, you can make them not to conserve. Actually,
Okay.
and there's a
Interesting.
connection with quantum mechanics. Yes, how it gets resolved in quantum mechanics. So yeah, so boundaries are very important. Actually, physical objects.
Very good. Very good. Yes.
Yeah.
Thank
Thank
you.
Thank you. And last question from Alexei Yanchishin.
Yes, I have a maybe very quick question about these conserved quantities. Why we want to conserve the phase space volume? Because you say that there is no any conserved quantities except of
No, it's not.
volume of
No,
phase space volume.
no, there's no phase space. If there's no Hamiltonian, but there's still a state space. There's still position and velocity, and it's just a simple calculation that in position and velocity space, even if you have a curl force, the volume is conserved. It's a kind of a generalization of Liouville's theorem. Of course, this is true only if, in the cases we consider, where the force is position dependent but not velocity dependent. But it's just a result, and I don't want it or not want it. It just is.
Okay, thank you.
Thank you. Good.
Okay, thank you. So we let us finish and let us thank again for inspiring talk and the power you give us to pass the dark times. And we hope, really hope to see each other in person next time. Thank you.
All the best. Thank you very much.